Hello and welcome to the session. In this session, we are going to discuss about solving linear programming problems with mixed constraints. In our earlier sessions, we had discussed about solving standard maximization problems and standard minimization problems using simplex method. Now, general linear programming problem is either a maximization or a minimization problem with constraints which can either be greater than equal to form or less than equal to form or equal to form. For example, maximize z equal to 11x1 plus 15x2 subject to x1 plus 3x2 is less than equal to 6 minus x1 plus 3x2 is greater than equal to 3, x1 is greater than equal to 0 and x2 is greater than equal to 0. This is a general linear programming problem having mixed constraints. Here, one constraint has less than equal to inequality and the second constraint has greater than or equal to inequality. Now we will discuss how to solve this type of linear programming problem. So now, this is a maximization problem. So, all constraints must be of less than equal to type. So, our first step would be change the greater than equal to constraint into less than equal to form by multiplying by a negative sign. So, here we have minus x1 plus 3x2 is greater than equal to 3 multiplied by negative sign. We get x1 minus 3x2 is less than equal to minus 3. So we have maximize z equal to 11x1 plus 15x2 subject to x1 plus 3x2 is less than equal to 6, x1 minus 3x2 is less than equal to minus 3, x1 is greater than equal to 0 and x2 is greater than equal to 0. As we solve a general maximization problem, the next step would be to add slack variables to the constraints to change them in equal to form. So we get maximize z equal to 11x1 plus 15x2 subject to x1 plus 3x2 plus s1 is equal to 6, x1 minus 3x2 plus s2 is equal to minus 3, x1 is greater than equal to 0, x2 is greater than equal to 0, s1 is greater than equal to 0 and s2 is greater than equal to 0, where s1 and s2 are slack variables. So we have the following equations: x1 plus 3x2 plus s1 is equal to 6, x1 minus 3x2 plus s2 is equal to minus 3, minus 11x1 minus 15x2 plus z is equal to 0. Its initial basic solution is given by x1 is equal to 0, x2 is equal to 0, s1 is equal to 6 and s2 is equal to minus 3. But this solution is not the basic feasible solution because we have basic variable s2 negative. So we need to find a feasible solution. Hence we follow step 3, in which we have to find or choose the pivot element. This is our initial simplex table. Now see here, we have negative numbers in the bottom row, but the new thing is that we have negative numbers in the RHS column, that is the right hand side column. In solving standard problem, we did not have these negative numbers in the RHS column. So, we will first deal with the negative numbers in the last column, irrespective of having negative values in the bottom row. Note that in solving a linear programming problem having mixed constraints, we may have all positive values in the last row or may have positive or negative values in the last row. We will not consider them, rather we will first deal with the negative values in the RHS column. Here we have one negative value, that is minus 3. To get rid of this negative value, we will pick pivot element using the following rules. First, choose negative number in the RHS column, leaving the last row entry. If you have more than one negative number here, then choose any one. Now, move to the left of negative number chosen and look for any negative number in that row. Now, if there are more than one negative numbers in that row, then choose any one of the negative numbers. The negative number chosen will give the pivot column. Now choose the pivot element by finding smallest test ratio. Now here we have minus 3 in the RHS column. We move to the left in that row. Here we have one negative number minus 3. We choose minus 3. So this x2 is our pivot column. So it is the incoming basic variable. Now to choose pivot element, we find ratio by dividing the elements of the RHS column by the corresponding element of the pivot column, leaving the last row entry. Note that we will choose only positive ratio. We have 6 upon 3 equal to 2 and minus 3 upon minus 3 equal to 1. So minimum of 2 and 1 is 1. Therefore, minus 3 is the pivot element. Also, S2 is the outgoing basic variable. Now our next step is to make this pivot element 1 and all other elements in the pivot column 0 using row operations as we have proceeded in standard problems. So we have the following table. Here x2 has entered the basis and we have divided the pivot row by minus 3. We get minus 1 by 3, 1, 0, minus 1 by 3, 0 and 1. Now to make other elements in the pivot column 0, we have to apply row operations on R1 and R3. R1 goes to R1 minus 3R2 and R3 goes to R3 plus 15R2. So we obtain the following table. Now see, in RHS column, we do not have any negative value. So we proceed with the same procedure. We look at the most negative value in the bottom row. It is minus 16. So x1 is the entering variable. For outgoing, we will look for test ratio. We have only one positive ratio, 3 by 2 equal to 1.5. So 2 is the pivot element and S1 is the outgoing variable. Now we make the pivot element equal to 1 and all other entries in the pivot column equal to 0 using elementary row operations. So we have the following table. Now all the values in the bottom row are positive, so we have arrived at an optimal solution. Given by x1 equal to 3 by 2, x2 equal to 3 by 2 and maximum value of z equal to 39. Now we discuss how to solve a general minimization linear programming problem. Suppose we have a minimization problem, for example, minimize z equal to 2x1 minus 3x2, subject to x1 plus x2 is less than equal to 20 and 2x1 plus x2 is less than equal to 70. We know how to solve maximization problem with less than equal to constraints. So, in order to solve minimization problem, we will convert the objective function into maximum form. by multiplying the objective function with a negative sign. That is, minimize z equal to 2x1 minus 3x2 is equivalent to maximize, say p equal to minus z equal to minus 2x1 plus 3x2. Or we have converted given minimization problem to maximize p equal to minus 2x1 plus 3x2 subject to x1 plus x2 less than equal to 20, 2x1 plus x2 is less than equal to 70, which is a standard maximization problem, and it will be solved as we discussed in our earlier session. Note that here we will find the maximum value of p, but we need to find the minimum value of z. So we will multiply the obtained maximum value of p by negative sign. Note that if there are mixed constraints in a minimization problem, then we first convert it in maximization problem and then proceed as we have discussed in this session, that is, method of solving linear programming problem with mixed constraints. In our earlier session, we had discussed how to solve the standard minimization problem by writing its dual. We can solve the same problem without writing its dual and solving by method of solving linear programming problem with mixed constraints. Here we will convert the minimization problem into maximization problem. Then we will write all the constraints in less than equal to form and will proceed in a similar way. If while solving a linear programming problem, we arrive at a situation where we are unable to find an outgoing basic variable from the table, for example, we have to choose the minimum ratio to find outgoing variable if all ratios are negative or undefined, that is, we are unable to find positive finite ratio, then the solution of the given linear programming problem is unbounded. So in this session, we have discussed about how to solve general linear programming problem with mixed constraints. This completes our session. Hope you enjoyed this session.